Welcome back to CS201 walkthroughs, and my name is Lukash, and today we're going to be talking about writing Turing machines. So here I've just copied over the structs from the Homework 3 document. I've copied over an example Turing machine from that document, and I want to walk through another Turing machine I wrote and talk through kind of my thinking and how I approached it. Before I go into that, I want to say it's a little bit confusing. It's of probably comparable difficulty to the one you'll be writing, or the ones that you'll be writing in your homework, and perhaps on, probably not, but perhaps on one of the exams. But it takes some time, and it takes some real elbow grease. I had a few errors in this. You'll probably have a few errors in writing yours that you have to go back and correct. It's totally fine. But stick with it. So here we go. This Turing machine I wrote to add 5 to an input binary number. So it starts on with the head on the left of a binary number in state Q1. Probably should specify that. Starts with the head on the left of a binary number of 1s and 0s in state Q1. And then it ends with the head on the right of that binary number plus 5. So just as you are allowed to in your PSET, your homework, I've used additional tape symbols just to make some of the techniques I use applicable to what you might be doing. So here I've defined tm add 5, and the way I approach these, or the way maybe that's best to think about them, is I think sequentially. The last few PSETs we've been thinking a lot about recursion and base cases and these kind of loop-de-loops and what's happening at each step, or each recursive call, 5 recursive calls later, how are we separating the car and the coder? We're not doing any of that here. Turing machines have loops, they can have loops, but they can also be thought of pretty linearly. So I basically I wrote out in comments kind of what the states are supposed to be doing at that point. And then it kind of just marches through them, and it says, okay, we're going to do this, we're going to do this, we're going to do this. There's an important loop that we'll get to, but mainly I would think that this kind of functions linearly. It doesn't recall it, the entire thing and start back at the beginning. Okay, we'll do this with an example, and I'll kind of look at what the configuration for that example looks like. So here my example is going to be the binary number 3. How about we do 4? Right, here is the binary number 4. If you don't remember binary, this is the 1's place, this is the 2's, and this is the 4's. Okay, so I'm just going to be writing out the tape at each step. So it starts in Q1 with the head over here on the first number. And here I say move to the right and add a marker X. So this is one of those additional tape symbols that I've decided to add. So it's in Q1. Whether it sees a 0 or it sees a 1, it's just going to move to the right and leave those alone and stay in Q1. Okay, so the head's going to be here, leave it alone, head's going to be here, leave it alone, head's going to be here. It goes over and it sees a blank. Here, how about I'll put it in here. Now we're at 1, 0, 0, blank. Okay, what does Q1 do when it sees a blank? Changes to Q2, prints out an X, and moves to the right. Okay, so this blank is going to turn in an X. We're going to move to a right and be pointing at this blank now. Maybe, well, yeah, so this is where our head is. Okay, let's see what the next part does. As I said, it writes out the number 4 in binary. So I used a few steps for this. It's not really much logic here, but it says Q2 sees a blank. Because we're on a blank, we know we just went to the very right most of the tape, and it puts a 1 there and moves to Q3. Q3 sees a blank, puts a 0 and moves to Q4. Q4 sees a blank, puts a 0 and moves to Q5, and then moves back left. So let's see where we are at the end of that. We had 1, 0, 0 in a comment. We had 1, 0, 0, X, and then we put our blank turned into a 1. The next blank turned into a 0. The last blank turned into another 0, and then our head is here because we went to the left after the last step. Okay? So the next part is moving back to the x. I just wanted to comment that in, even though it doesn't take a lot of mental power. Q5 stays in Q5, moves to the left, whether it's a 0 or it's a 1, and it only changes to Q6 when it hits an x. You may notice that I'm not writing out all the instructions for every state. Like up here, for state 2, I only wrote what to do if it encounters a blank because I know it'll never encounter anything that's not a blank. Same thing for 3 and 4. Here for Q5, I also know it'll never hit a blank because it's moving within this section of the tape here, which won't have any blanks. Okay, so we move back to the x. The tape is going to look the exact same. It's going to leave everything alone and switch to Q6 when it hits the x. Our tape is still going to say 1, 0, 0, 1, 0, 0. And now our head is pointed at this x. Now I'm saying adds 1 to the right. So here we get into the real meat of this method. My plan is to add 1 to this number we started with on the left, and then subtract 1 from the right. Add 1 to the left, subtract 1 from the right, add 1 to the left, subtract 1 from the right, until the right becomes 0. Okay, does that method make sense? So this is 4 now. I'm going to make it 5. I'm going to change this 4 to a 3, change this 5 to a 6, then 2, 7, 1, 8, 0. And when it's 0, I'm going to stop. Okay, that's my way of adding 5 total to this side over here. It starts as 4, but I'm adding 1 before I ever subtract from here. And then I'm subtracting 4 times and adding 1 to the other side each time. 1 plus 4 is 5. When I add that 5 on to this 4, I should get 9. Well, let's see, this will turn from 4 into 5, and then I'll do that 4 more times. Yeah, I'll get 9, right? Right, should get 9. Which looks like, what is that? It's an 8 and a 1, is that right? There's the 1s, the 2s, the 4s, and the 8s. 8 plus 1 is 9. Okay, so that works. Or hopefully that works. So that's my method. To do that, I have to add 1 to the right. Now we have to understand a little something about adding and subtracting in binary when you can only look at 1 digit at a time. So let's move down here and let's think a little bit about adding and subtracting in binary. Adding in binary we can do by finding the rightmost 0, changing it to a 1, and changing all the following 1s to 0s. So this is a little confusing, but let me give a couple examples and maybe it'll make sense. Here's the number 5 in binary. I can go until I find this 0, change that 0 to a 1, so now I have 1, 1, and change all the 1s after it to 0s. So now we have 1, 1, 0. This is 6. The reason this works is because you can't add to a 1. A 1 is the maximum digit in any column. It's kind of like if I were adding 1 to 999. Well, you would say I can't add it here, I can't add it here, I can't add it here, I have to add it at the very end. And then you would change all these to 0s. Okay, so sort of the same thing. Let's do one more example. Here's the number 1010 is, let's see, that's 10, right? So I would find the rightmost 0. The rightmost 0 here is this 0. I would just change it to a 1. 1, 0, 1, 1. Obviously that's 1 more because I've added 1 in the 1's place. Okay, let's go through the last example. Let's do 1, 0, 1, 1, 1, 1. I don't know what that number is, but I know the way I'm going to add 1 to it is by changing this number to 1, 1, 0, 0, 0, 0. So I change this 0 to a 1, and then everything after it into a 0. That's just how you count in binary, right? If I were to count a number higher than this, it would be 1 followed by all these zeros. Same way that one number greater than 99 is 100. You add in that extra digit and it's the lowest possible that a 3-digit number could be. Here in this case, the lowest possible a 5-digit number can be is 10000. I hope that made some sense. For subtracting, we do something similar. We find the first 1 and change it to a first one from the right and change it to a 0. Then we change all subsequent or all following zeros to ones. Okay, so let's have an example. Here's an easy example. This is 1 plus 2 plus 4 is 7. To subtract 1, we just do that. Right? Find the rightmost one, change it to a 0. There are no ones after it, so we're done. Let's have another example. Let's try that. Here we go. This is 10 again. To subtract, I said find the rightmost one, so this. Change it to a 0. So that'd be 1, 0, 0. And then change all following zeros to ones. So this 0 then becomes a 1. There we go. And this is 9. Right? A 1 here, and this is 8, which makes 9. Okay, so how did I implement that up here? I said I'm going to add 1 to the right. I do that by going left whenever I see a 1, and then when I hit a 0, I change it to a 1. So that's what we said over here, right? Find the rightmost 0, change it to a 1. So I'm saying go left until you find a 0, change it to a 1, and then switch to Q7. When I'm in Q7, all I do is go right, and I'll change all of the following ones into zeros. Like as we said, change all the following ones to zeros. There's another important note here, is that I say if Q6 encounters a blank, also change to Q1, but make that blank a 1. So say I'm trying to add 1 to 111. If I'm doing this on my Turing Machine tape, I'm going to go left, left, left. I'm going right. I'm looking for the rightmost 0. Since there are no zeros, it's going to encounter this space, which is a blank. It should change that blank into a 1. Okay? So when we're doing addition in our Turing Machine setting in Racket, we have to keep into account that blanks at the beginning are basically the same as zeros. Alright. So then I go back to the X. I say when Q7 hits the X, change to Q8. Now I'm going to check if 4 is 0 yet. This is going to be my way to break out of the loop. Okay, so let's update this, I guess. So we said we're going to add 1 to the right. So we were here. When we add 1 to that, we're going to hit a 0, change it to a 1, change to Q7. This is the first 0 we're going to hit, so we're going to get 1, 0, 1, x1, 0, 0. It's going to change to Q7. Q7 is going to go to the right until it hits this X. It's going to hit Q8, go to the right again, and now we're just pointing at this. Okay. So maybe I'll put that here too. 1, 0, 1, x1, 0, 0. And we're looking at this 1. So the way I'm going to check if the 4 has turned into a 0, so if I'm done with my function, or if I'm done with my Turing Machine, I guess, is if I've already subtracted this number down to 0. If you remember my method, I said I'm going to subtract 1 from this number on the right as I add to this number on the left. Alright, so if this number is 0, that means I'm done, and I've already added 5 to this number on the left. So check if the 4 is a 0. All I have to do there is see, are there any 1s over here? If there are any 1s, it's not 0 yet. So Q8, if it sees a 0, goes to the right. If it encounters a 1, it moves to Q9, and we're not yet done. If we're done, we're going to hit a blank, because this is going to be all zeros. Q8 will skip over all those zeros and then hit a blank, in which case I've said go to Q10. Okay, so this is this is an if statement, right? This is my way of saying if we are done, go to Q10. If not, Q9. So you might be thinking, you probably aren't thinking, but doing if statements is an important feature of coding, and something that you're going to have to do in your Turing machine. So you're going to have to do something differently based on what the input is. This is your way of doing that. is you can pass to different states depending on what you see. And here I see that my number on the right is either finished or not finished. It's either 0 or not 0, and then I pass to a different set of states in each case. So here I have my set of states if I'm not yet done, and if I am done, then I go to these set of states. Right? So first let's handle these. I said if we go to the right all the way, which means that our number on the right over here is completely 0. It isn't yet, but if it was, we would be done. And all we have to do is basically erase this and print out the stuff on the left. Alright, so I say change all those zeros to blanks, change the x to a blank, and you're done. Alright, there's no Q11, so Q11 is our halt state. Q11 is halt. If we're not done, then I go back. I go back through my loop. So for in Q9, we have more to do. Subtract 1 from the right. Okay, so Q9 first finds a 1, then changes it to 0. I won't over-explain it, but it's the same subtracting method that we talked about down here. Finds the first 1, change it into a 0, and then we pass to Q12, which loops back to Q5. Okay, so when we go back to Q5, if we look at what that says, it says move to the X. So our loop is, if we're not yet done, we go back, we move to the X, and we keep adding to the left and subtracting from the right until we are done. So let's kind of walk through where we would go from here. I'll do it below so we don't have the code in the way. So where we're here, we should go to the right, and we should add 1. Right? We should go to the left. We should subtract 1, which says turn this 1 into a 0, and then turn these into 1s. We should add 1 to the right again, which goes like that. Subtract 1 from the left again, which goes like this. Oops. Add 1 to the right, which does that. Subtract 1 from the left, which does that. Add 1 to the right, which does this. Here's what the space is. Subtract 1 from the left, which does this. And add 1 to the right again. Or sorry, add 1 to the left. And then we go over here, we see we have 0. We turn all these things into blanks. And then we stop here with 9. Okay, I know that was confusing. I know it might have been hard to follow. Go ahead and watch it again if you need to. Go ahead and look through this code as much as you'd like to. I'm also going to show you that it works. So yeah, I'm not showing you the homework 3 solution document, but I've copied my tm_add5 in, and I'm going to run simulate light. I've traced it so we can see the output. So here's my starting configuration. I'm going to start it with the number 4, and I'm going to let it go. Oh, I mistyped it. Oh, I didn't give it the starting state. Let's try again. The starting state is Q1. Okay, now let's let it go. You can see it working. We can see it go back and forth. There's the X. It's going back and forth. And we have 9. Great, right? We started with 4. Now we have 9. Let's try an even tougher one. Let's do like, what number is that? This is 1 plus 4 plus 8 gives us 13. So we want to output, I forgot again. Right, so this is 13. Make sure we're starting in Q1. We want to output 17. It's doing a lot of work. You can see it if you look carefully. You can see it doing that addition. So here, is this 17? Well, let's check. This is oh no, we want 13 plus 5 is 18, right? So this is a 2 plus a 4, 8, 16, that's 18. right? 1s, 2s, 4s, 8s, 16s, which gives us 18. And if you look, it's going to be a little bit hard to see. But if I scroll back through the trace, you can kind of see if it's doing its work. So here's let me scroll back even further. So here's the state at which we have 3 left on the right, and our number on the left is, this is the 2s, the 4s, the 8s. So here we have 14, right? So it still has 3 more, or I guess 4 more to add. It might be in the process of adding one to the left. If we scroll down, we can see, okay, now it's added one to the left. Now it's going to go over to the right and subtract one from the right. Bam. Subtracted one from the right. Okay, so now it's going to have to go back and add one to the left again. Let's scroll down. Oh, it's getting there. Oh, it encountered the blank, which means that it needs to add a 1. So here it adds that 1. Now there are 5 1s. It's going to change all these to 0s. Okay, it goes back and changes those to 0s. So there, added 1 to the left again. Now it's going to go over to the right and subtract 1. There we go, subtracted 1 from the right. Okay? I know that might have been a little hard to follow. I promise that once you write some out on your own, it'll get a little bit easier. Really quickly, I want to talk a little bit about TM stepper. So this is one of the Turing machines that you might have to write, or that people have had to write in the past. Takes a positive binary number and produces an output string of x's of length equal to the binary number. If you think about what we did up here, you can probably do that in a pretty similar fashion. For TM stepper, it asks you to write a function that outputs a Turing machine. So it takes an integer and returns a Turing machine that runs for n steps. And the clue I'll give you is that, well, let's see. If I have, say, the number 5, and I want to write a really simple Turing machine that runs for 5 steps, how about I just do something like this? I'll say, well, Q1, so it says it also runs on a completely blank tape. So it's easy for me to just say, okay, you see a blank, change to Q2, leave it as a blank, move to the right. I'll just do this with, well, I guess, 4 states, right? Because I'll go 1 to 2, 2 to 3, 3 to 4, 4 to 5. Oh no, so I need 6 states. 1 to 2 is 1 step, 2 to 3 is 1 step, or 2 steps total. 3 to 4 is 3 steps total, 4 to 5 is 4 steps total, and 5 to 6 is 5 steps total. Okay, so I need 6 states. Q2 will pass to Q3, Q3 will pass to Q4. I'm not going to write them all the way out. Q4. And this sounds like something I could probably do recursively. Oops, I forgot one. So what would be my formula for an instruction, right? All I have to do is recursively cons instructions onto a list. And then I have to output that list of instructions, right? So this is a recursion problem. All right, I hope I've given you some idea of how to write Turing machines, how to approach TM stepper, and how to do well on homework 3. Thanks for watching this walkthrough. Thanks for bearing with me through that tough explanation of this example Turing machine. As always, please come into office hours, post on the Piazza, or email the CS201 help email with questions. Again, thank you for watching, and I hope to see you in the next video.